I return to our simplified Hamiltonian, and I want to make some observations here. The electron is only about 1/2000th of the proton mass, and what does that tell us? It tells us that the mass under forces moves a lot more slowly than the electron. And since the electron is attracted to the proton doesn't appear to move much, and the electron moves the most. An exaggerated example is if this is an apple and this is the Earth, the apple falls towards the Earth, but the Earth also is attracted up to the apple. But we never think of it that way. So this isn't quite the scale of Earth and an apple, but it does kind of the same effect. And here's the idea is that if we consider that the mass, as large as it is compared to the electron, doesn't move, then if it's not moving relative to the electron, then it doesn't have any kinetic energy. If it doesn't have any kinetic energy, then these terms can go to zero. And also, if the r's are not changing, the masses are not moving, then this just becomes a constant. This method is referred to as the Born-Oppenheimer approximation. And here I've got it all laid out. You notice it's a lot simpler. And in place of the RAB, which is the repulsion, that just becomes a constant. And so we just put R down there. The wave function now depends on two variables, R1 and R2. Each of those is in a three-dimensional space, and that's why we got 6 dimensions. The R is separated by the big R is separated by this semicolon, which shows that it's not a variable, but it's a constant. For stretched H2 molecule, it doesn't work so well because the energy of the bonding orbital, the attractive part to those protons, starts to decrease because they go farther away. R gets bigger and the attractive force becomes less, and the energy of the anti-bonding orbital increases, the repulsion term between the electrons. And this acts like two independent atoms, or approaches looking like two independent atoms. And this reveals two different energy surfaces. Now that term might not make much sense, but at least we've got two different things we have to deal with, and it becomes a superposition of configurations. And so even this approximation that makes life simpler doesn't always work, and we have to keep that in mind as we go to more and more complicated molecules and the interaction between multiple atoms. You might notice in this playlist that the videos are getting very short, and they're very self-contained, so that if something doesn't make sense, you can replay it again, and I hope that helps your understanding. Next, we're going to molecular orbitals, which now we're getting down to brass tacks. You'll find in that video that just tracking the electrons is not enough. Instead, we have to look at all the potential orbitals and then figure out occupation numbers of those. In other words, which orbital has an electron and which doesn't, and what are all the possible configurations. So that's where we're headed next.